the cosmic background, the CMB, as the probe, which was predicted by Alpha and also Herman in 1948. They calculated the high energy radiation field would cool and with expansion of the universe to about like 5 Kelvin today, which is the cosmic background. And when that happened, the universe was very young. It's about like 3 × 10⁵ of its current age. So it's like the baby state of the universe. And then if we take a closer look, how this happened was because this is on the left of this plot. It's kind of a pie or pizza slice of the universe if we look out. So at the very beginning, the universe was very hot and also dense, and it expands and cools down to the extent that, to a state that the universe was kind of filled with photons, electrons, and also protons. Electrons and also photons are closely coupled because electrons is charged. And then, so they are like a plasma. They are very opaque. We cannot look through them. And then once the temperature of the universe cools down enough, the electrons and also protons, they start to combine to neutral hydrogen. The photons are kind of released because it doesn't interact with neutral hydrogen anymore. It goes all the way across the universe to us being observed as a CMB. So there is a good analogy made by the WMAP team, was basically like we are looking to the sky and then we see the clouds. So even though there are long distance between us and also the edge of the clouds, we don't see it because it's transparent. We just see the edge of the clouds, analogous to CMB we are seeing to the history, to the early universe. So then after this was predicted, it was actually detected in 1965 by Penzias and Wilson. It's a very exciting moment. On the bottom left is actually a very famous picture of Penzias and Wilson in front of their instrument, which is the Holmdel horn antenna at Holmdel, New Jersey. This picture on the right is one picture of it I took during a trip there. So it's still there. It's in New Jersey, not far away from us. So if you want to go check out it, I definitely recommend it. It's a really cool thing. So this horn antenna, you can see it's a horn, but the size of this horn is really hard to maneuver. So they cleverly designed this with a kind of with a kind of a mirror, so it reflects the thing 90 degrees. So you can just spin it to observe at different elevation. And then from their observation, the discovery of the CMB, it really provided us the probe to study the beginning of the universe. And then after decades of efforts, eventually the COBE satellite, which was launched, I think early 1990s or late 1980s, basically started to characterize the properties of the CMB after the discovery. So the one very exciting thing is it found the CMB in terms of frequency spectrum, it is a perfect black body. The measurement was done so well, you can see the error bar here, 2.725 plus or minus 0.001 Kelvin. And the error bar for each of the data points along this black body power spectrum, the black body spectrum is shown here, but it's really small. It's only 1% of the line thickness. So it's a very well done measurement, and also it reflects the perfect black body spectrum of the CMB. So if we come back, think about it. So this is probably the most accurate black body spectrum we can ever measure from nature, but it actually comes from the most ancient light. That's another remarkable thing about CMB, was because CMB was emitted when the universe was really simple. Everything is linear physics without all these nonlinear astrophysical effects. So it's just a pure moment for us to study the cosmology and also physics. So that's the spectrum. So this is actually not trying to distinguish any places around the sky. And then the next question will be anisotropy, whether if we look at different positions on the sky, whether they have the same temperature. Penzias and Wilson tried this in 1965, but their measurement didn't show any kind of anisotropy because of the limitation of the instrument. But that's kind of an odd thing, because when the CMB was emitted, the horizon at that time was really small. It's even smaller than this little circle I'm showing here when we observe the sky today. So which means at that time, distance beyond this horizon should not have any causal connections with each other. So they should not have the same temperature. They should not even know the existence of others across this distance. But it turns out to have the same temperature, which is really odd. So that's called the horizon problem. To solve this problem, in 1980s, there comes out this cosmic inflation theory, which describes the universe went through an exponential expansion at the very beginning, like 10 to the minus 35th seconds after the Big Bang. How it solves the problem? It basically, this dramatic kind of expansion expands the causal the horizon much larger than the horizon we can observe today. That's why in our observable universe today, everything seems homogeneous and also isotropic. So beyond this, inflation also predicts several other things, which one of them is the flatness, which because of the dramatic expansion, any kind of initial curvature of the universe will be kind of diluted. It's like the Earth is so big, we know it's round, but locally we cannot see it. And then another thing that is really remarkable to me is it predicts initial perturbation that comes from quantum fluctuations that was blown out to the astronomical sizes. That's actually will be the seeds for all the large scale structures for today of our universe today. Another thing we'll predict is actually we will not observe any kind of topological defect relics in our observable universe, because the density of that is highly diluted. So these are the phenomena. So how do we calibrate that or characterize that? The amplitude of inflation is parameterized by the tensor to scalar ratio, which is R, and it is set by its energy scale, which can be as high as 10 to the 16th gigaelectrovolts. That's the level of the grand unified theory scale. So comparing to the largest collider we can achieve on Earth, which it goes up to 10 to the 3rd gigaelectrovolts, is more than 1 trillion times higher. So this is kind of the grandest experiment we can do in the universe. And the current limit was set by the bicep Keck and also Planck data. R is less than like 0.06, 95% confidence interval. And so, but there is a canonical single field slow roll inflation model. It predicts R should be around 0.03 to 0.05. So right now we are standing in a very kind of interesting position in this field that when we push further, we will either detect inflation or we'll rule out a very important group of models. And then let's see what we know right now. So, okay, inflation was proposed to solve these problems, and then it also predicts something, and then we can see whether what it predicted is verified. So after that, after the Penzias and Wilson anisotropy measurement, they didn't see anything, and then COBE satellite carried another instrument to try to measure the anisotropy of the CMB. It kind of discovered it, but it was not sensitive enough to characterize it. Then that was followed by another space mission, which is WMAP, which gave us actually the very famous anisotropy measurement of the CMB. So today, the state-of-art measurement is actually given by the Planck satellite, which is shown here. And then here is the state-of-art full sky CMB temperature anisotropy measurement. And then what are we going to do with this? Just looking at it doesn't tell us too much. We need some like scientific way to analyze this data. So for people doing CMB, normally what we do is we do it in power spectrum. So it's similar to once we have a musical instrument, we play a note, and then if we transform the acoustic oscillation into frequency, and we have a note frequency, we have a bass frequency, and we have harmonics. And then, but this is a Fourier transform in time, going from time to frequency. Same idea for the CMB, except right now we are in a sphere, so we do Fourier transform in angular space, in spherical harmonics, actually. So and then we also have the same thing. Instead of having frequency, we have multiple, we call L in space. So the lower the L value is, the higher the angular scale it is. The higher the L value is, the smaller the angular scale is. It's a kind of confusing, but I will try to make it clear as possible. And then you can see it's similar. You can see we have some like plateau here at the very low L, large angular scale, and then we have some acoustic peaks going up and down, which encodes a lot of information we will talk about more later. So the reason we have this acoustic peak is like I'm showing a plot here. It's like assume we have a still water, and then we have a water drop here. And then 1 second after the water drop, we'll take a picture. This kind of perturbation can only go that far. That's kind of the scale of this. Because when CMB happened, the universe is at a finite age. So the perturbation can only go that far to exhibit itself at its base mode and also its harmonics. Okay, let's see how can we get all these parameters out of this plot. So right now, the kind of a standard mode of cosmology is called ΛCDM. Lambda is kind of the cosmological constant. CDM stands for cold dark matter cosmology. It has 6 parameters. I will walk you through how this plot, this power spectrum itself, can constrain all of them. So when when people were looking for this temperature anisotropies, the big question is kind of like what we are doing for the B mode. What we are doing for the inflation is we don't know the amplitude of it. It can be 0.01, it can be 0.001, it can be whatever. So when people were starting CMB, nobody knows what it is. So this level of this plateau is very important. It can be 1,000 micro Kelvin square. It can be 1 million. It can also be 10. It could all be possible. And then it was measured. So this level is actually pretty important. It sets the amplitude of the primordial perturbation in the early universe. Beyond that, this kind of tilt that is fitted here is also important. It's almost flat, you can see, but it's not quite. That's another actually prediction from inflation. So now we have A sub s, N sub s, one is the amplitude, one is spectral tilt. And then this is the largest angular scale. And also another thing we can get out of the largest angular scale of this is actually the optical depth to the reionization. And then we come to the higher multiple region, which we have these acoustic peaks. And then let's see, how do we do this? So you can see the data points, we can measure the peak position very well, which corresponds to angular scale on the sky. And then from the physical model, we can know at the time when CMB happened, what is the scale in physical size, which is delta chi. And then this is also measured by delta theta by the position of the peak. So we can do some very simple calculation, which is whether delta chi equals delta theta times dA, which is the angular diameter distance. If they do, it's a flat universe. If it's not, it's either positive or negatively curved. So it turns out within the error bar, they equal, which means the universe is flat. And also another thing we can use is actually the amplitude of the oscillations. The oscillation comes from the matter, mainly gravitational interaction. So the amplitude of these oscillations encodes information of the matter fraction of the universe. And then you can see this is the first peak, this is the second peak, third and fourth. They are actually they carry different information. So basically the even and versus odd peak amplitude encodes the baryonic or normal matter fraction, because a simpler picture is you have matter collapsing. A dark matter doesn't push back, but the baryonic matter does push back. That's why we have this even kind of even oscillations. So all together, we from this CMB measurement, we can basically try to come up with this basic components of the universe, which is we have like 5% of ordinary matter. We have dark matter, which is about 26, 27%, and then the rest will be like 70% dark energy. This is how this CMB power spectrum can give the entire picture of the Earth universe, or entire universe. So, and then we can come back to see how the cosmic inflation is doing in terms of different predictions, etc. So flat geometry checked out. Almost scale invariant perturbation spectrum is also checked. And there's another adiabatic perturbation I did not have time to mention. It also checked. So there's one thing that is left, which will be the B-mode polarization in the CMB. This is what everyone is after these days. That's why it's called the Holy Grail in the modern cosmology. So I was looking for a Holy Grail picture, and I found this from Indiana Jones. So he chose wisely. Let's see what we can do with ours. Okay, so we can measure this from the CMB polarization anisotropy. CMB is polarized by quadruple anisotropy through Thomson scattering. And then if we map the CMB polarization pattern, and then we can decompose that pattern into two modes. One is the E mode you can see here. One is B mode here. One is parity symmetric, the other one is not. If you flip it, one becomes itself, the other one becomes the other one. So, and then only tensor perturbation, which comes from inflationary gravitational wave, that can generate the largest scale B mode polarization. That's the smoking gun measurement that it can come from. So if we do detect why cosmic inflation is so important, because it is intrinsically, it is a quantum gravitational process. So several years ago, LIGO detected gravitational wave. It was a sensational event, but it was only two black holes. So if we detect this, this would be kind of a universe scale and also quantum gravitational wave process. So it would be kind of a even grander scale gravitational event being detected. So even Rainer Weiss at MIT, who is one of the founding fathers of LIGO, is very excited about this. He said he thinks this is a remarkable thing to do. And now how do we do it? So if you look at this power spectrum on the right, on the top is the E mode, on the bottom is the B mode. So the E mode, you can see the amplitude is actually higher. It's about 20 or something microkelvin square, but the B mode is much fainter. So right now, after years of work, we can see different experiments have already made good measurement on the E mode power spectrum, but people are still pushing down on the B mode. So if you take a closer look on the B mode, we can see there are kind of two components. One kind of goes up, is the dotted line goes up in this high L value. This is actually the lensing B mode, which is kind of the lensing effect that lens the much brighter E mode into the B mode. That will be a contamination for our detection. But if we go to the low L, which is a large angular scale, if we come here, we can see this is one of the peak we can use. This is definitely the peak we can use. This is clean. So, but it's really hard to go to the large angular scale. So that's where people are pushing down, I'm pushing left. So, and over the past decades, the ground-based CMB experiments have made so much progress and has become the driving force of this field. So they are all clustered in kind of two sites. One is the Chilean site, one is the South Pole site. The South Pole site has South Pole Telescope, SPT here, you can see. and also BICEP Keck telescope within these two ground shields. This talk will be focusing on the Chilean side because this is what I'm more familiar with. So this is another zoom in picture of the Chilean site. We have CLASS, we have ACT, we have Simon's array, and we'll soon be joined by SO. This site is really high. It's 5,200 meters high and very dry. So it's very good for CMB experiments. That's why it's home to several of them. So I will talk about the ones I'm involved one by one. First, let's talk about the ACT, which stands for Atacama Cosmology Telescope. So ACT is a 6-meter telescope, very big, and it provides arc minute level resolution at 150 gigahertz to probe basically high L around this range science. So ACT is probably the first CMB experiment that went to the plateau. That's why it has gone through generations of instruments. The first one is ACT. It only studies temperature, but with high resolution. The second generation was ACT Pole. From its name, you can see it became polarization sensitive. And then the next one, which is the current operating one, is called Advanced ACT Pole. It was trying to go not only polarization sensitive, but large angular scale polarization. So this is a picture of ACT. And then I'm on the right, I'm showing a picture given by Planck collaboration, which is a really cool demonstration, I think. It basically put the temperature power spectrum, the E mode power spectrum, and also the B mode power spectrum together in one plot. So you can see actually how much progress we've made over the years. So at the beginning, nobody knows where the temperature power spectrum was. The upper limit was around like here. And then we pushed down, got over it. We got temperature power spectrum very well measured. And then we pushed through the E mode as well. And right now we are pushing to the limit of the B mode. So, and then if we emphasize, and also this actually a collaborative effort, this you can see different data points represent different experiments all together, providing this overall picture. So if we emphasize the different generations of ACT, you can see the first generation covering the high L, only temperature sensitive. And then the next generation pushing deeper in sensitivity and also be polarization sensitive. And then the current generation is basically also definitely pushing deeper with higher sensitivity and also pushing to the left, trying to recover the larger angular scale. So why is that? Why is the direction? It's good. It's easy to understand. We want to go deeper, more sensitive, but why do we want to go to the larger angular scale? I hinted a little bit, but I want to emphasize this again. That's because if you want to recover, if you want to measure the B mode from the inflation, we have to go there because otherwise the lensing will be dominating. There was some like delensing techniques, but they are not the cleanest measurement. So you can see lensing peaks around here. And then on the left, we can see we have the inflationary B mode at different amplitude. You can see at 0.1, 0.01. Right now, it seems like R is not 0.1 anymore. So if we push lower and lower in terms of the amplitude of this signal, we need to go even further left. You can see here. Probably for 0.1, we can go around like here, but for 0.01, we have to go around here. That's where the next experiment I want to talk about, CLASS, comes in. So CLASS stands for Cosmology Large Angular Scale Surveyor. So it's an array of small aperture telescopes for multi-frequency observations. There were 4 telescopes. You can see from this picture, 2 mounts. Each mount houses 2 telescopes. So in 2 plus 2 is 4. So and then a technology CLASS employs is the front-end polarization modulation technology. This actually guarantees the CLASS's stability of the instrument to recover the largest scale of the sky. So that's why CLASS is very unique in the sense that is sensitive to the largest angular scales in the sky. So if you use this plot again, so this is where we had for ACT Pole, Advanced ACT. CLASS is basically pushing, CLASS will not be sensitive to the large angular to the small angular scale, the high resolution ones, because it's a small telescope, but it's aiming to go after this lowest L, largest angular scale on the sky. And now this is the logo we developed, trying to represent the shape of the telescope. And then right now ongoing, there's another ambitious Simon's experiment, Simon's Observatory, where we have a lot of collaborators at Yale as well. So this is actually a combination of large aperture telescope, similar to ACT, and also several small aperture telescopes, similar to CLASS. And then combining all cutting edge technologies, including dilution refrigerator to cool things really down, and multi-frequency observation, also polarization modulation technologies. So eventually, Simon's Observatory will have 3 small aperture telescopes shown here, 1 large aperture telescope shown here. The proceeding we just put out this week was basically talking about the receiver within this large aperture telescope. This is our logo. So you can see if we use this plot again, so Simon's Observatory will cover the entire parameter space here, basically with a combination of large aperture telescope and small aperture telescope. But still, Simon's Observatory is not aiming to go to the lowest L. So that's why eventually, with all the data from different experiments, we can come back together, put all this data together collaboratively to recover the B mode Earth spectrum we're after. Like what we are showing here already, I plunk different experiments together, put this picture together. And on the horizon, there's another even more ambitious experiment called CMBS4. It's basically doubling the capacity of SO scale. So it will have 2 sites. One is South Pole, one is Atacama Desert, where we've been talked about for a while. It will basically have 2 large aperture telescopes, 6 small aperture telescopes, mainly at the South Pole. So I'm using the Simon's Observatory rendering here, but the design will be different. So, so now with the combination of the space mission and also ground-based experiments, now we have a good picture of what the universe, the evolution, the history of the universe. So I think until now, we can convince people that cosmology is a serious subject. So basically, we started from quantum fluctuations, and then after some inflationary period, and then all the fluctuation was extended to the cosmological scale, and then CMB was emitted and goes all the way across the dark ages, and then different stages of the universe until it was observed by our telescopes, double mapping in this case, because they made this plot. So you can see it's a long way from the CMB photons being emitted to it is being observed. So it does carry a lot of information on the way. That's what we can use. So beyond cosmology, there are a lot of other sciences we can study. One of them is with the CMB measurement to constrain the evolution of the universe very well, plus some other data sets, we can constrain the sum of neutrino masses to about like 15 millielectronvolts. That is, I would say, 4 sigma detection, even for the inverse hierarchy, neutrino hierarchy. So beyond that, from the Sanyet-Davdovich effect, we can discover tens of thousands of galaxy clusters. These are the most massive structures in the universe, and then we can get tens of thousands of them. And also because CMB came from redshift of 1100, so it's actually everything in a way can be used as a lens. So it's actually CMB lensing is a good way to measure the integrated mass in the universe. And also locally, because we live in the galaxy, everything we look out will be the galaxy first, which is a trouble for the cosmological study. But the data set itself can be used to study the galactic dust and also the magnetic field very well. So this is actually from Planck collaboration. This is the galactic large angular scale magnetic field from the 30 gigahertz synchrotron radiation. And also recently, we have been looking at, because of the high cadence scan strategy from the CMB telescopes, we have been looking at transients in the microwave sky. Eventually, we are thinking probably we can try to find a planet 9 even. So there are a lot of other sciences we can do beyond cosmology. So when I was looking at this plot, there is something very obvious to me that we did not do anything about it yet, which is dark ages. This is the uncharted land with dark ages here. So it's that's why I kind of thought along this direction and eventually joined the 21 centimeter collaboration. So the dark ages is a very important period of time in the evolution of the universe, because it actually it's the gap between the CMB and also the late universe. Both we have observed very well. And also in terms of the evolution of the universe, as we mentioned earlier, when the CMB was emitted, the universe was almost homogeneous. The anisotropy, although we kept talking about it, it was only a 10 out of a million. It's very homogeneous. And then when we observe galaxies in a late universe, we know, like also today, the universe is very inhomogeneous. We have the star, and we have a solar system, and then we have the outer space. Orders of magnitude different. So how did this transition happen? It happened in the dark ages. We don't have any handle on. So, and also another interesting thing is CMB is a surface. It's like the cloud analogy. We can only see one surface of it. But for the dark ages, it's actually a volume we can study. It will contain more information for us. And also, dark ages is kind of a transition between the homogeneous to very inhomogeneous nonlinear stage. So it will contain some linear physics, especially at the beginning of it. So it will be very easy to understand, to study. It will be cleaner than the nonlinear physics region. So that's another benefit that we can take advantage of. But the reason that we haven't done anything yet was because it's really hard, because after the CMB was emitted, the universe was basically filled with hydrogen atoms not doing anything, basically. They don't emit, they probably absorb a little bit, which we'll talk about, but it's just really hard. We don't have any signature. Another example, we don't have a probe to do it. But yet. So there is a way we can do it, which is by 21 centimeters. So 21 centimeter is actually a hyperfine structure transition from hydrogen atoms. So hydrogen atoms is very abundant in the universe, like 3/4 of them. And also it's very simple, we know it very well. This kind of transition from the hyperfine structure is very well measured, probably one of the most precisely measured quantities in lab. It's about 21 centimeter in wavelength. And also another very cool thing I want to emphasize here is it's a narrow line. It probably doesn't strike you too much at the first sight, but if you think about it, so CMB, no matter which frequency we measure a part of the black body spectrum. Still one surface. But this narrow line signature, if we measure it at different frequency, we actually measure it at different redshift, which means it's a different distance from us, which means it's a different slice of the universe. That's why we can measure instead of a surface, but a volume. So to study astrophysics with 21 centimeter was first predicted by Van der Haast in 1941, around the same time with the CMB prediction. And then it was first detected by Edwin Oscar Purcell in 1951. Here is a picture of how they did it. It's another horn antenna, Edwin Purcell horn antenna at Harvard. So this doesn't exist anymore, so we cannot go there and visit it. They literally use a horn antenna structure set up, and then with the receiver and stick into a window of one office. The individual parts exist. This horn antenna is still in, I think it's Green Bank Telescope, Green Bank Observatory. And this building, which is the Lyman laboratory in Harvard still exists. The window exists still. So if you want to visit them, we still can. So the 21 centimeter signal has already helped us to understand a lot of astrophysical things. One of the famous one was actually, we used that to measure the rotation curves of our galaxy, which eventually as one of the strong evidence of dark matter. So, and then let's see how we can use it. So this is actually a good plot made by Harrow collaboration, basically illustrating this. So on the left, CMB, so Planck can measure that. On the right will be the galaxies where JWST, all this kind of telescopes can observe the high redshift galaxies when they are all kind of fully evolved. It is this region when the during the dark ages, first stars, reionization, that is a little bit fuzzy for us right now. So they would, and that's why Harrow comes in. So there were two directions we can do it. One is spatial anisotropy. It's very similar to what we do with the CMB. We basically measure the anisotropy and then we take power spectrum. I won't emphasize on this too much, but the bonus point we get is, as I mentioned, we can measure volume from the frequency space. The redshift frequency actually gives us the kind of the line of sight information of it. Let's first take a look at this direction, the line of sight redshifted frequency direction. We call it the global 21 centimeter signal because it's global. We don't distinguish the anisotropy in the redshift direction. I put it here as an analogy. It's kind of similar to the CMB black body spectrum. We measure it in the frequency space. So this is a good illustration from Pritchard and also Liu in 2010. So this is actually on the top is kind of a picture of how the universe evolves. And then on the bottom is what the signal will be like. So one question I haven't answered now is the hydrogen atom still doesn't emit. How do we observe it? So then the answer is we use the backlight, which are the CMB photons. We still observe the CMB photons, just try to track its interaction with neutral hydrogens. So you can imagine the measurement for that will actually be the deviation from the CMB photon temperatures. And then if you look at that, so this is from theoretical model that at the very beginning we'll have some dip because there was some absorption from the hydrogens, and then it will come back and dip even more when the heating begins. And when the heating reionization begins, we will have emission from the hydrogens, and then we come to no signals after reionization ends. So these are all based on our theoretical predictions. However, Hedges in 2018 measured a trough around this frequency range. Very exciting. However, the depth of the trough is around like 10 times higher than the prediction. So there was some like speculation. That's why we are all trying to verify that, including our current work in Harrow. So this is along the line of sight, redshift direction. And then let's take a look at the power spectrum, the spatial anisotropy direction. I'm also putting the CMB power spectrum here as an analogy to make it easier for us to understand. So right now, the focus is on detecting signals on the epoch of reionization as a first step. So this plot is actually made by one of our collaborators in University of Washington, starting this GitHub repo. It's very nice. You can check it out if you're interested. So this is basically the predicted theoretical power spectrum is around here. We're showing 2 here. And then the current limit is given by these different lines above here. So yeah, as mentioned earlier, because with 21 centimeter, we can do this in multiple redshift. That's why these different upper limits are color-coded with different redshift information. So the first generation, these upper limits are from the first generation experiments, including MWA paper. And then the ongoing ones are the second generation experiments, learning from the first generation experience and lessons, basically aiming to make detections, pushing this upper limit down to make detections of the epoch of reionization. That will be the first step of eventually pushing into the dark ages measurement. If we can really push through the reionization and probe into the dark ages, that will give us a lot of information. It will tell us the evolution of the universe. It will help us to understand the large scale structures and even constrain the cosmic inflation. It will dramatically constrain the cosmological parameters we have today. And more importantly, it will be the on-site of 21 centimeter precision cosmology. CMB has been doing so well, establishing the foundation, but 21 centimeter measurement has the potential to push it even further. So now it kind of brings to the end of my talk. This is the conclusion here, like I just said. So CMB has been doing well with the combination of space mission and also ground-based experiments, and 21 centimeter has the potential to push it even further. There's one thing I want to mention at the end is, so just think about the history. 30 years, around 30 years from now, no, 30 years ago, we did not even know that CMB was a black body spectrum, not even to say the anisotropy being measured. And 30 years afterwards, right now we stand at 2020. For my generation, for me, it's kind of hard to appreciate that at the time we did not even know the CMB anisotropy and also its black body power spectrum. And then if we borrow the same idea to apply it on 21 centimeter, maybe in 30 years, in 2050, the entire thing will be so routine. So young scientists at that time will have the same kind of confusion as I have right now, saying, oh, I cannot believe in 2020, people are still wondering about what is this? This is that. So whether this will happen, I have to ask different people. Different people has different opinions, but I would like to stay positive on this. I think we'll get there as long as we believe in it, as long as we push it down. We keep pushing it down. So yeah, that's all I have to say. Thanks.
So thank you, Zhilei. I really enjoyed the talk. Do we have any questions or anything from the audience? You can feel free to speak up or put your questions in chat.
Yeah, I have a question. So it's very nice talk. I think it was a very nice overview for someone like me, not really involved in this kind of cosmology. So
thanks.
Once you have this 21 centimeter and you can push the redshift beyond, so you had this very nice figure with the, I think just maybe a couple slides back. It was the redshift, yeah, this one. So you have these kind of sort of inverted towers that you have some feasibility to do the measurements. So what is the reason why there are like gaps in the middle in this experimental data? Is it a way to kind of extend that further?
Gap, you mean gap on here or gap between the detection and also?
No, gap between this, and then why can't we sort of make it, push it in the delta square, kind of make it flat? It might be a little naive question.
Oh, you mean why it is kind of zigzagging?
Yeah,
because that gets to the weeds of it. The different experiments will publish different constraints at different, because some of these are actually, a lot of them are actually interferometer arrays. So they are actually sensitive. The sensitivity for different scale will be different. Does it make sense? And also in the data analysis, probably some of the data was not high quality enough. They just threw it away and they don't want to publish it. So a lot
but these are all basically extracted from the power spectrum, right?
Right. So they are measured at different K value, which will be what they are sensitive to given their instrument configuration.
I see. Okay.
Yeah, the first generation experiments was more like a pathfinder. So there were a lot of intrinsic challenges.
No, it's very cool concept overall. Thanks.
No problem. So this plot was made by one of our collaborators, Brina Hazelton in University of Washington. She's very good.